Hello, everyone. Welcome to another wonderful day of chemistry. So, today we're going to go ahead and try and figure out how we can use our knowledge of acids to help determine the pH of a solution. And to do so, we're going to use a lot of our tricks from equilibrium. So, if I'm going to try and look at the acidity of a solution, the real true metric of that is going to be the amount of hydronium or protons that's going to be produced whenever I put an acid into water. Now, if I'm going to do this, well, I have a reaction, I have an equilibrium constant, I'm going to need an ice table. So the simplest approximation we can do is we're going to assume that we've got no conjugate base and no hydronium under the initial conditions. So my only thing present in solution under the initial conditions is going to be my acid. So in truth, it's important to note that we are going to have low levels of hydronium already present from water. However, since these concentrations are about 10 to the negative seventh, we should be safe in a lot of cases by assuming it's pretty close to zero. The next approximation we're going to end up making is going to be trying to determine whether the acid is going to be weak or strong. So let's go ahead and go with the simpler case. Let's assume I've got a strong acid like nitric acid. So if I'm working with nitric acid, well, that's a pretty big K. So let's go ahead and assume that the reaction goes to completion so that my nitric acid will completely disassociate. So if I've got a one direction reaction, I can then assume that my hydronium concentration is going to be about 6 molar. And we can illustrate this by walking through the ice table. So first of all, water is going to not be present. I've got initial concentration of 6 molar nitric acid, 0 molar everything else. I'm going to be consuming my nitric acid and producing equal amounts of nitrate and hydronium. So then, if this reaction goes to completion, I know that I will consume all of my nitric acid and my resulting concentration should be 0. And I'll be presenting, again, equal amounts of nitric and hydronium. Well, if I've got no nitric acid left, that means my X has to be 6 molar. And thus, I should have a resulting solution that's 6 molar in nitrate and 6 molar in hydronium. So this gives me a hydronium concentration. Then I can go ahead and, using this relationship, say that anytime I've got a strong acid, my equilibrium level of hydronium will be the same as my initial concentration of strong acid. We're going to use this a lot. So then, now they've got my hydronium concentration, I can go ahead and calculate the pH as negative log of that concentration. And it turns out this gives me a pH of negative 0.8. Now, this often throws people off, assuming that pHs, they have to be between 0 and 14. Well, in general, pHs will be between 0 and 14, because the only way to get a pH that's less than 0 is if you have more than 1 molar of a strong acid. Not something you encounter regularly. However, you can often edge pHs into the slightly negative numbers, but rarely less than about negative 2 or 3. So if you end up doing this, what it's going to end up showing is that we're going to have a fairly low pH under these very acidic conditions. So whenever we're trying to figure out the pH of a strong acid, we're going to start with this idea that the initial amount of strong acids should release an equal amount of hydronium. So then let's go ahead and try and determine the pH of some other solutions, like 0.1 molar nitric acid. So if I do this, this means that my hydronium concentration should be 0.1 molar, equal amounts of protons is released. Then putting that into pH, it should be negative log of that 0.1, which gives us a pH of 1. So whenever you're mixing a 0.1 molar solution of any of your strong acids, we're going to assume that the pH is going to be about 1. Now, let's go ahead and try and figure out the pH of 10 to the negative 8th molar nitric acid. Well, using what we previously assumed, this should release about 10 to the negative 8th molar protons. So then I go ahead and you determine the pH of this solution. Negative log of 10 to the negative 8th is 8. This gives us a slight problem. This indicates that if I add a small amount of a strong acid, I will increase the pH, as in make the solution basic. That doesn't quite track. And this is a good illustration of one of the approximations we made. If I've got a neutral water that I'm adding this nitric acid to, it should have a background concentration of 10 to the negative 7th molar hydronium. Oops, that's actually more than the protons I released. So what we need to do is acknowledge that water disassociates in these cases. And we'll talk about some tricks of how to do that later, but I want you to be aware of this big approximation. So in general, it's only going to be really accurate to make this assumption that that a strong acid perfectly disassociates and we can use just that number of protons if I've got a solution that is greater than about 10 to the negative 6 molar of a strong acid. However, anything less than about 10 to the negative 6 molar or 1 micromolar of a strong acid is fairly worth ignoring. So just keep that in mind that if I'm dealing with more than 1 micromolar of strong acid, we can go ahead and use this approximation. Otherwise, the amount of acid added will be relatively negligible. Now, that was for strong acids, but what if I have a weak acid? Well, under these cases, now I actually have to acknowledge my equilibrium constant. So to do this, we're going to make use of our good old friend, the ice table. And now I actually have to plug in my initial concentrations. So again, I'm going to continue ignoring the influence of water because it is a liquid and will not show up in my equilibrium constant. If I start, I'm going to assume that I will have no starting amount of acetate or free protons. Then I will consume acetic acid to make acetate and hydronium. And then I can find the equilibrium amount. It should be X for both hydronium and acetate and 0.1 minus X for acetic acid. So my hydronium concentration can then be solved using the equilibrium constant. So in this case, my equilibrium constant is again products over reactants. So I have X times X, so X squared over 0.1 minus X. This is a classic dissociation reaction. However, unlike most dissociation reactions, this gives me a quadratic equation, which is generally going to be of this form: X squared plus the equilibrium constant times X minus the initial concentration of my acid times the equilibrium constant. So this works. We can go ahead and use a quadratic solver, your calculator, the good old quadratic equation. But in practice, we don't want to do this all the time. So what we can often do is use our approximations and assume that our equilibrium constant is going to be relatively small, which 10 to the negative fifth it is. And if our equilibrium constant is relatively small, we're only going to be producing small amounts of acetate and small amounts of hydronium. So our X is going to be relatively small. So when we do this, we can assume that our initial concentration of acid will be relatively unchanged. If X is small enough, then my denominator will stay as 0.1. We can go ahead and drop this term. And then in this case, it makes solving for X a lot easier. My hydronium concentration will be the same as X, and that can be given as the square root of 0.1 times our equilibrium constant. Plug in our numbers, and we end up with a proton concentration of about 1.3 micromolar, so a very small amount. So in this case, 0.1 minus 0.0013, yep, I think it's fairly safe to assume that our approximation was correct in this case. Then we can go ahead and use our proton concentration to solve for pH. So plugging in our number, it turns out this gives a pH of about 2.89. So this is again fairly acidic. If you were going to taste this, it would be quite sour. So when we're going to go ahead and try and determine the pH of an acidic solution, we're going to use several different key procedures. So the first of which is if we've got a strong acid, we're going to assume that the amount of acid, the concentration of acid we added is going to be the concentration of protons. Again, watch out as this can break down for acid concentrations less than about 10 to the negative 6 molar. However, if I've got a weak acid, what we're going to need to do is use a full ice table to determine the amount of protons released. Now, the big assumption is we're going to start by assuming that the initial amount of protons is 0. Yes, this can break down under certain circumstances. But under those occasions, we're not going to have a very acidic solution anyways. Then we're going to assume that X is going to be, if it's going to be relatively small, we can use a simplified ice table. However, we will run into cases where this approximation won't be quite so good. And in those cases, what we're going to need to do is use the quadratic equation to actually determine for the real amount of hydronium produced. So using these basic approximations, we should be able to find the pH of most common acid solutions. However, this focuses just on the amount of protons being released. However, oftentimes we care about that ratio of the amount of conjugate base formed versus the amount of acid we added. We're going to go ahead and look at this percent ionization next time. Till then, take care.